right, in question number 3, we've got Lance Armstrong. Travels at an average speed 48 kilometers per hour. What distance does he travel in 3.5 hours? So we're looking for the distance. So the distance should be speed times time. And our substitution is 48 kilometers per hour. Multiply that by 3.5 hours. 168 kilometers. Part B, well, the race covers a distance of 240 kilometers. How long would it take Lance Armstrong traveling at 48 kilometers per hour to complete the race? We're looking for time. So delta T is going to be distance over speed. And so the distance here is 240 kilometers. And then, of course, the time is found by putting in 48 kilometers per hour here. Now, you can put your units in if you want. And then you're going to notice that the final unit at the end is 1 over hours, which happens to be hours. So 240 divided by 48 gives me 5 hours. Now, if you look at the significant digits here, we have, of course, 2 significant digits, 3 significant digits that we're looking at. So 5 hours would be the preferred answer there. Okay? Because what I'm doing is I'm looking at each number and figuring out how many significant digits it has. And each of these has 3 significant digits. Okay? All right, I'm guessing you tried the practice problems number 1 to 3, so let's take a look at what we're doing next here. Well, the practice problems here, I'll just bypass those. Hopefully you tried them out. And let's look at plotting distance time graphs. So you probably had some experience plotting graphs, making sure that you're putting in your data appropriately, where you have time on the horizontal and distance on the vertical. So first thing you want to do is you want to set yourself up a scale. Scale has to work to go at least up to 6. And so when I set this up, I'm going to think about, well, can I do every 4 units or something like that to go with every one? Probably. Something like that would be fine. So 1, 2, 3, 4, 5, and then 6. Okay, now we've got our time set up. Let's take a look at the distance. The distance here, I have to at least go up to 33, so I'm thinking about going by, I don't know, I don't think there's 33 going vertically there, so I'm going to have to go maybe every 2 units, right? In other words, 2 per division. So I'm like 2, 4, 6, 8, 10, so I might be 10 here. 2, 4, 6, 8, 10, we've got 20. And then 2, 4, 6, 8, 10. We have 30 right here. Okay. And 2, 4, 6, 8, 10. I can put in 40 here. Now I know it's maybe not as vertical as it is horizontal, but that's okay. Let's plot out what we can here. So we have 1 second going by. Sorry, 0 seconds going by. We're at 6 meters. So 2, 4, 6. So the point should be right here on the axis. 0 over and 6 up. Okay. I like to circle my data points so that I really kind of emphasize where they are. Otherwise, I might lose sight of them on the page. At 1 second, we're at 10.5. So this is 10. The next division would be 12 up. So 10.5 would be 10 up and a quarter more. Okay, try and estimate it if you can. Now we're looking at 2 and 15. So 2 and 15 means we're at right between 10 and 20. That's a good location for it. Now 3 at 19.5, we're really close to 20. That'd be the location. 4 at 24. And you can try this out, just double check that you're getting the same locations I am. 5 at 28.5. Right there. And 6 at 33. Now sometimes it's nice to do a double check to make sure that they're all just right above those divisions that I set up. And now a line of best fit is kind of essential here, right? You try and balance the points above and below, try and get that trend line, okay? pretty much goes through all of them. It's pretty close to a nice fit there. And if you look in general, they went up by 4.5 meters every second that went by. So a straight line probably is pretty appropriate there. Okay? Now when you do a slope of this kind of graph, then really what you're doing is you're finding out the speed of an object. So I can do the slope by using some of the points that it's going through here. Okay? All right, speed of the object in the graph above. So let's take a look at this page here and get the speed. You can see it's about 4.5 meters per second by just kind of looking at the chart, but it's nice to be able to get it right off of the page here. So what I'll do is I'll pick 2 points that are nice and easy to read on the graph. Let's do that in kind of a different color so you can see it. There would be a good location right there, and this would be about 1.25 and 12 up. Okay? Let's find another location where it looks like it's going straight through, like there. That's a good spot. That's going to be 5.25 and up at 30. Okay, so I'm just going to stay on this page, and then I'm going to copy it down on the next page, just to, at least the answer. So I've shown my work right here where the graph is. So the slope is going to be the following. So what we do is we look at the y-coordinate 2, which would be 30, subtract y-coordinate 1, which would be 12. So I'm going to have 30 take away 12. Then I'm going to divide that by 5.25 take away 1.25. Now if I put my units in here, I have meters for the numerator and seconds for the denominator. So 30 take away 12 is 18. 18 divided by 4 has got to be 4.5. Okay? So on the next page here, I can just say, well, it's 4.5 meters per second. Now, when it says compare the following graphs, such as this kind of thing, like what's really happening in the graph? Well, you can see car A, right? So looking at car A, some time started elapsing and it's going a certain distance. And so we'd say it's moving at a constant rate away from some reference point. Okay? So moving at constant speed, or you could say velocity in this case, but constant, away from a reference point. Take a look at what car B is doing. Like no distance is covered and time keeps moving along because it's a flat horizontal line, so it would be at rest, which means stationary, it means not moving. Car C, that's doing the same as car A, but the line's not as steep, so it's a slower rate of motion. So same as car A, but slower. Okay? Now, when we talk about the idea of speed, we like to interchange kind of velocity when it gives the direction, and that's really what D is about here. It's starting away from a reference point, and then it's coming back towards it. Okay? So in this case here, it is essentially, and I mean, it's kind of a balance between car A and car C, how fast it's moving, but it starts, right, away from the reference point, and moves towards it at constant speed. Speed is what they're supposed to say. So what does the steepness of the line tell you? Well, you kind of answered part A right there. But the steepness of the line in part B tells me how fast the object is moving. What does the direction of each line tell you? Whether it's going towards the reference point or away. if it's moving towards the reference point, pardon me, if it's moving towards the reference point, it has a negative slope. Moving away from the reference point would be a positive slope. It's not as easy as you might think, making a video and talking at the same time here. And I never really will be a movie star. It's pretty obvious. All right, we're going to continue along right away here. Hang in there, everyone.